Okay, so here we go. We are doing, I am not here today, so I am teaching day 7, and we will go through with this. Here we go. Normal approximations for binomial distributions. So there is a rule. You're going to use it a ton in the future, so I think it's a good idea to go ahead and do it now. Suppose that the count x has a binomial distribution with n trials and the probability of success is p. As a rule of thumb, we will use the normal approximation when n is so large that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. We call this condition large counts. You're going to see during chapter 8, 9, 10, we're going to do tons of large counts. So to use a normal approximation, you must check large counts. Okay, that's a new one coming to us. So this first question is going to be great because it's going to tie into that. In a survey of 506 teenagers, show that the distribution is approximately binomial. So first of all, B, I, N, S. B meaning their success and failure. So they're asked if they have a debit card. So you have two options. They can say yes, they can say no. So that satisfies the binary part of binomial. I is independent. So the rule for independence is that you cannot sample more than 10% of the population. So our population would be all teenagers between the age of 14 to 18. So I would have to say that 506 is less than or equal to 10% of all teens 14 to 18. And I would that's very easy to say that there's more than 5,060 teenagers. So boom, that's a check. Next is the number of trials is set. Well, they're going to ask 506 teenagers, so 506 trials, ding. And the probability of success. Well, they told us success is 10%, so 0.10 is yes, 0.90 is no, and it's always constant. So this clearly is a binomial distribution. So check the conditions for using a normal approximation. Well, I can approximate this normal distribution or binomial using normal if it satisfies large counts. So remember up here at the top, this is the formula for large counts. N times p is greater than or equal to 10. N times 1 minus p is greater than or equal to 10. So n is 506. P is 0.10. So that is 50.6, which is greater than or equal to 10. So check. That part of it is satisfied. And then I'm going to do 506 times 1 minus 0.10. So that's failure. And 506 times 0.90 is 455.4, which is greater than or equal to 10. So check. So large counts is satisfied. Therefore, normal is appropriate. Okay, so I'm allowed to use a normal distribution to approximate this. So use a normal distribution to estimate the probability that 40 or fewer teens in the sample have debit cards. So first of all, I need a mean and a standard deviation. And if you'll remember for binomial, the mean is n times p. So that's 506 times 0.10. So my mean is 50.6. And the standard deviation is the square root of n times p times 1 minus p. So that is the square root of 506 times 0.10 times 0.90. 506 times 0.10 times 0.90. And I'm going to square root that. So that's 6.75. All right, so here's my curve. 50.6 is my mean. I'm going to do norm, CDF. We want to know that 40 or fewer. So if this is 40, then this would be fewer. So norm CDF, my lower is negative 10,000. My upper is 40. My mean is 50.6. And my sigma is 6.75. So negative 10,000, 40, 50.6, and 6.75. And the answer is 0.0582. So 0.0582 would be the proportion that would have is a probability that 40 or fewer teens in the sample have a debit card. So we can see that 50.6 is the mean, the standard deviation is 6. So if you think about, you're going down to like 43 and 57 or 58 for one standard deviation. So it makes sense that as you get to 40, you're getting really far left, and that is a small probability. It's not crazy tiny, but it's pretty small. All right, next question. So the birthday game. So I had to read about this before I started teaching it. So I'm going to tell you what it is. So you have a teacher, and the teacher generates a number that goes to the day of the week. So like Monday is 1, Tuesday is 2, Wednesday is 3, Thursday is 4, da da da. Okay. And the students have to pick the day of the week that the teacher randomly generated. And every time they miss, they get another homework question. So if they get it on the first trial, or no, for every guess, they get a homework question. So if they get it on the first trial, they have 1. But if they don't get it on the first try, they have to try again, so then they're going to have 2. And if they have to try again, they're going to have 3 homework questions. So the number of homework questions they have is how many guesses that it took for them to get it right. So 1 guess, if they get it right the first time, they still have 1 homework question. So this is saying, why is the number of guesses it takes to correctly match the birthday, which is the day of the week? So is this a geometric setting? So the answer would be BITS. So they are either right or wrong. So that's binary. Independent, well, the teacher is using a generator to generate the day. So generator shows independence, right? Because it won't be like, oh, I picked Monday last time, so I'm going to pick something different. It just generates. T is they guess until success. And S is their probability of success. Well, if they're 7 days in the week and they're picking a day, they have 1/7 is their probability for success. And that means that 6/7 is failure. Okay, so check, this is a geometric distribution. So question 2 says, find the probability that the class receives 10 homework problems as a result of playing the game. So when I think about 10 homework problems, I'm thinking, okay, they had 9 wrong guesses, then they had 1 correct guess. So to find the probability of 10 homework problems, the probability that x equals 10, that means they got success on their 10th attempt. That is 9 wrong attempts. So failure, which is 6/7 9 times, times success, which is 1/7 1 time. So without using the geometric PDF button, I could do 6/7 to the 9th power times 1/7. So I got 0.0357. Now, let's go ahead and check it with a geometric PDF. So Geomet PDF. So I'm going to go into my calculator and go second vars, and I'm going to go down to Geomet PDF. And it's a PDF because this is an equal to 10. So that's why it's a PDF. PDF because of the equal to. So all I need is my probability, my number of trials. Okay, so my probability of success is 1/7, and it took them 10 trials. So 1/7, 10 trials, paste, and the calculator gives me 0.0357. So exactly what we got by hand, the calculator's doing for us. Okay, the next one says find the probability that y is less than 10. So for y to be less than 10, then that's telling me it is really the probability that y is less than or equal to 9. So less than 10 guesses is really 9 or less. So remember, you have to have that equal to because your calculator does work on the equal to. So I'm going to do Geomet CDF, and I'm using a CDF because this is an inequality. So second vars, Geomet CDF, my probability of success is 1/7. My number of trials would be 9. So 1/7, 9, I have 0.7503. It says interpret what this value is in context. So the probability of the students taking 9 or less guesses to correctly guess the day is 0.7503. So you can tell that's a cumulative because it's 9 or less. So it would be adding up 1 plus 2 plus 3 plus 4 all the way up to 9. So that's what less than or equal to 9 is. All right, next, suppose you roll a pair of fair 6-sided die until you get doubles. Let t equal the number of rolls it takes. So show that t is a geometric random variable. So B, so for binary, you either get doubles or you do not get doubles. I, so when you're rolling dice, each roll is independent. The die do not change. T, you're going to roll until doubles. So trials are not set. And S, your probability of success is 1/6 is doubles, 5/6 is not doubles. Okay, so perfect, boom. Next, find the probability that t equals 3. So that is a Geomet PDF because it's equal to, so it's a PDF of x equals 3. So when I go to second vars, Geomet PDF, my probability of success is 1/6. I'm back on that other question. 1/6. My x value is 3 tries. Okay, so 1/6, 3 tries, paste. So there is a 0.1157 chance that they will get it on the third try. So exactly third try. So interpret this result in context. So I would say, like, if you roll many, many times, if you roll many, many times, there is a 0.1157 probability you will get doubles for the first time on your third try. And you could say on average. Oh, on average. Love that. Okay, because that's your wiggle room word. In the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability this happens. So, now how is this different? Well, it's within 3 terms. So it's a probability that x is less than or equal to 3. So, instead of being a geomet PDF, it is geometric CDF. So we have geomet CDF. So second vars, I'm going down to geomet CDF. My P is still 1/6. My X value is 3 trials. And that's 1/6, 3 trials, paste. So it's 0.4213. So there is a 0.4213 that they will get doubles within their first 3 spins. So maybe their first spin, their second spin, or their third spin. Okay, so we have homework 50. I'm going to move on to homework 50. All right. When an opinion poll calls for residential telephone numbers at random, only 20% of the calls reach a live person. You watch the random digit dialing machine make 15 calls. So find mu sub x. Well, mu sub x is n times p, so that is 15 calls times 20%. So 20% of 15 is 3 calls. Next, find standard deviation of x. Well, the standard deviation of x is the square root of n times p times 1 minus p. So that's the square root of 15 times 0.20 times 0.80. So 15 times 0.20 times 0.80 to the 0.5 power. 1.549. Perfect. So a federal report that a lie detector test given to truthful persons has the probability of 0.2 of suggesting that they're deceptive. A company asks 12 job applicants about theft from previous employers. Using a lie detector to assess their truthfulness, suppose that all 12 answer truthfully. Let x equal the number of people who lie detectors say are being deceptive. So mu sub x is 12 people times 20%. So 2.4 is my expected number, long run, of every 12 you ask that are truthful. Approximately 2.4 are what we expect to come back and say that they're lying. Standard deviation of x is the square root of 12 times 0.20 times 0.80. So I have 1.386. 1.386. All right, there are 20 multiple choice questions on an exam, each having 4 possible responses, of which one is only correct. Each question is worth 5 points to answer correctly. Suppose that a student guesses the answer to each question with their guesses from the question being independent. The student's expected mean score on the exam is, so there are 4 possible responses, so my probability of success is 0.25, and 0.25 times 20 is 5. B. There are 20 multiple choice questions on the exam, the standard deviation. So same question, but standard deviation. So I'm going to say the number of questions is 20, success is 0.25, failure is 0.75. So 20 times 0.25 times 0.75 to the 0.5 power. I have 1.94, so my answer is B. Next, for which of the following choices N and P can we not use the normal approximation to the binomial distribution? So remember, it's large counts, which says that n times p is greater than or equal to 10, n times 1 minus p is greater than or equal to 10. So I'm going to do 25 times 0.6 and 25 times 0.4. So 25 times 0.6 gives me 15, and 25 times 0.4 is 10. So this checks out. Then I'm going to test 40 and 0.4. So 40 times 0.4 and 40 times 0.6. So 40 times 0.4 is 16. So this is 24, check. This one checks out. So it's this one, because 0.9 times 60 is good, that's 54. But 0.10 times 60 is only 6. So that fails large counts. One way of checking the effect of undercoverage, non-response, and other sources of error in a sample survey is to compare the sample with known facts about the population. About 12% of American adults identify themselves as Black. Suppose we take an SRS of 1,500 American adults and let X be the number of Blacks in the sample. What are the expected number of successes? So if there's 1,500 in the sample and we expect 0.12, 1,500 times 0.12 is 180. So, using the expected number of successes and failures, does this meet the conditions for using a normal approximation? So my answer for this would be yes, because n times p is 180, and n times 1 minus p, and instead of n, I'm going to actually put the number, because 1,500 times failure, 1,500 times 0.88 is 1,320. They're both greater than or equal to 10, so large counts is satisfied. Okay, so using the normal approximation to find the probability the sample will contain between. Here we go. So 180 is my mean, and we want to go 165 to 195. So I want this. So I'm going to norm CDF. My lower is 165. My upper is 195. My mean is 180. My standard deviation I haven't calculated yet. So my standard deviation is the square root of 1,500 times 0.12 times 0.88. So 1,500 times 0.12 times 0.88, and I'm square rooting that, so it is 12.586. 12.586. That's my standard deviation. It was not given. You have to calculate that when they give you the question. So second VARS, norm CDF, my lower is 165, my upper is 195, my mean is 180, my standard deviation is 12.586. Paste. So my answer is 0.7667. So that's using a normal probability model to approximate a binomial. And it's okay as long as large counts and is satisfied. And you'll see on AP exams that they'll provide this as an extra optional correct answer. Next, is X a binomial random variable? So let's see, what kinds of websites do males aged 18 to 34 visit most often? Half of male internet users in this age group visit an auction site such as eBay at least once a month. A study of internet use interviews a random sample of 500 men aged 18 to 34. Let X equal the number in the sample who visit an auction site. Okay, so success is an auction site. Failure, no auction site. So that's yes. Each is independent, so we can guess that each male is independent, and 500 is less than or equal to 0.10 of all males. 18 to 34, so I'm happy with independence. N, so we have 500 as our trials. And our probability of success is 0.5. Because it said half, so they're telling you your success is half, 0.5. So find the mean. So mu sub x is 0.5 times my sample of 500, so that's 250. Find the standard deviation of x. So my standard deviation is the square root of 500 times 0.5 times 0.5 again. So 500 times 0.5 times 0.5 to the 0.5 power. So it is 11.18. So can we use the normal approximation to estimate the probability? So I'm going to say yes. 0.5 times 500 is 250, and 1 minus 0.5 times 500 is 250. They're both greater than or equal to 10. So large counts is satisfied. All right, use the normal approximation to find the probability that at least 235 of the men in the sample will visit an online auction site. So this is 250, at least 235 would be all of this. So I'm going to norm CDF, my lower is 235, my upper is, is 10,000, but I'm thinking, I wonder what difference it'd make if I made it 500. My mu is 250, and my sigma is the standard deviation, which is 11.18. Second vars, norm CDF, 235, 10,000, 250, and 11.18. So 0.9102 is what I expect. All right, next, I'm seeing how many questions there are. Oh, that's it, I'm about done. Okay, so next, engineers define reliability as the probability that an item will perform its function under specified conditions for a specific period of time. A certain model of aircraft engine is designed so that each engine has a probability of 0.999 of performing properly for an hour of flight. Company engineers test a simple random sample of 350 engines of this model. Let X equal the number that operate for an hour without failure. So success or failure. So the engine will either succeed or it'll fail. Each is independent, and 350 is less than or equal to 0.10 of all engines. So it's safe to say there's 3,500 engines. I think that's reasonable. N is my number of trials is set, it's 350, and S, my probability of success is 0.999. So find the mean. The mean is 0.999 times 350, 0.999 times 350, which is 349.65. Find the standard deviation. Well, it's the square root of 350 times 0.999 times 0.001. So that is 0.5913. Can we use a normal approximation to estimate this probability? Explain. So I think my answer is going to be no, because 0.999 times 350 is huge. 0.999 times 350 is 349.65, which is greater than or equal to 10. But failure, 1 minus 0.999 times 350 is tiny. It's 0.35. it is not greater than or equal to 10. Therefore, normal approximation is not appropriate. Okay, so you should not be using a normal approximation here. So, this says 2 engines failed the test. Are you convinced that this model of engine is less reliable than it's supposed to be? Compute the probability that x is less than or equal to 348. So I'm going to go binom CDF, second vars, binom CDF. My number of trials is 350. My probability of success is 0.999. My x value is 348. So 350, 0.999, 348. So there is a 0.0486 chance that this happened. So I would say, are you convinced that this model of engine is less reliable than it's supposed to be? I will say yes. If the engine is 0.999 reliable, then the probability of 2 failures is 0.0486. Because this was unlikely due to the small probability, but actually happened, it must be that the engine is not as reliable as they say it is. So when something that's highly unlikely to happen happens, then we say, wow, something's weird, because this should never have happened. So, of course, there is the chance it's the fluke, and, you know, this is just barely under 5%. But when something that's unlikely to happen happens, then we say, wow, something must not be right in the original calculations, because this should never have happened. That's what it means to be significant. When a number is small enough that it makes you look back and go, wow, maybe this isn't as fair or consistent as they're saying it is. When that happens, you have significant results. Okay, so I hope you guys have a fantastic Thanksgiving. All right.